Hi everyone, welcome to the class once again. I hope you're all doing good and in the best of your health. So already we have done the first 5 questions of this chapter, Thermal Properties of Matter, based on JEE Advanced Pattern Exercise. Those very interesting questions, and we have solved how variety of questions can be framed in this chapter. Now we'll be continuing from the 6th question, where the questions will be of single choice, multiple choice and integer type. Let's go ahead with the 6th question of the day, and the first question of the session. 3 discs ABC have radii 2 meter, 4 meter and 6 meter respectively are coated with carbon black on their outer surface. The wavelength corresponding to maximum intensity are 300 nanometer, 400 nanometer and 500 nanometer. So it's given that you have 3 discs, they are coated with black, that means they are acting like a black body. That means you can actually use it for, as per Wien's displacement law, you can use lambda m into T equals to B, that's constant, and then you can also use the power emitted, that is the rate of energy which is emitted by the surface is sigma a T to the power 4, that is what you can use. Next, the power radiated by then are QA, QB and QC respectively. It's given that the rate of energy emitted or the power emitted is QA, QB and QC respectively. So option number A, QA is maximum, option B, QB is maximum, C, QC is maximum, and D, QA equals to QB equals to QC. Now see that it's given that all the 3 are of different radii. You see that it's a disk, they are of different radii. If they are of different radii, it means they will be having different surface area exposed. Next thing you see here, it's also given that the wavelength corresponding to maximum intensity are 300 nanometer, 400 nanometer and 500 nanometer. For maximum intensity, you can actually use it for Wien's displacement law, that lambda m into T equals to constant. So what I will do, I will go and use 2 equations, first from Stephen-Boltzmann law and also from Wien's displacement law. So from Stephen's law or Stephens-Boltzmann law, we know that Stephens-Boltzmann law, we know that the power emitted Q is equal to sigma a T to the power 4. This is what we know. So what we can write that Q is proportional to A into T to the power 4. This is what we can write straight away. Sigma will be constant for all the 3 surfaces, and that will be same because all 3 are acting as black bodies. It's coated with carbon black. So sigma will be same for all the 3 bodies. So that's why I have replaced sigma and I have written the proportionality as it's proportional to A and T to the power 4. Next thing you see that from Wien's displacement law, we all know that lambda m into T is equal to constant. This is what we know. So from here, can we write that T will be proportional to 1 upon lambda m? Lambda m I am writing that is for the minimum value of lambda, that stands for lambda m, so T will be proportional to 1 upon lambda m. Now here in this case, the rate of energy emitted or the power that is emitted by each of the plate, that is Q that we have written, can we write Q is proportional to A T to the power 4, and instead of T to the power 4, can we write that as 1 upon lambda m to the power 4 by replacing T proportionality as it is inversely proportional to lambda m. So we can write using this 2 equation, Q will be proportional to A divided by lambda m to the power 4. We can write in this way because T is inversely proportional to the lambda m. Next you see, we need to, it's given that their radii are is 2 meter, 4 meter and 6 meter. This is given the radii for A, B and C. So if I draw the 3 discs, they would be represented something like this. This is A, this is B 4 meter and this is C, that is of 6 meter. So radius of A 2 meter, radius of B 4 meter, radius of C, that is 6 meter. Now you see here what we can do. 2 surfaces will be exposed, but 2 will be again, it will be common for both. So I am going to use this area that will be proportional to r square. Area will be proportional to r square, that is pi r square, that is the area, it will be proportional to r square. So we can write Q will be proportional to r square divided by lambda m to the power 4. This is what we can use for each of the values. Now I'm going to use this result and I'm going to write it here. I hope that you would have taken note of all these things that I'm rubbing. Next thing, Q is proportional to R square by lambda m to the power 4. So we can write Q is proportional to, for QA, it will be equal to R of A is 2 and the lambda m, the minimum value of lambda, the wavelength corresponding to maximum intensity are 300 nanometer. That's for maximum intensity. We have been given that its value is, I'm putting here 2 meter 2 whole square, and here for maximum intensity the lambda is 300 nanometer. So 300 nanometer power 4. Everything is given nanometer, we can use directly in this way. Then again you see here it's given 300 and it's given here 400, it's given here 500. So can we use for the proportionality, QA will be proportional to 2 square divided by 3 to the power 4. It will come out to be 4 by 81. QA will be proportional to 4 by 81, and here we can use directly now equality, or let me use here QA will be equal to proportional to 4 by 81, that is what we can put. Similarly for QB, if we use for QB, that will be proportional to, again, radius of B whole square divided by maximum intensity lambda, that is given as 400, so 4 to the power 4 we can use. 4 to the power 4 we can use, and here you will be having for the radius of B whole square, if you do, that is 4, so 4 whole square. So you will be getting this as equal to 4 whole square, 4 to the power 4, that will be 4 to the power 2, so 1 by 16 you will be left with. Next thing, QC, if I mention 6 whole square in the similar manner, and here you will be having 5 whole square, so 36 by, this will come out to be 36 by 625. So you'll be getting this. Now clearly now it's only thing the calculation part is left. If you do, this will come around 0.05, you'll be getting this. This will be around 0.06 something, this will be 0.0575. So what I'm going to do, comparing all the three, QB will come out to be maximum. The simple calculation that we can make an approximate calculation, this will be approximately 0.06, this will be 0.05, this will be 0.0576 something. You'll be getting this. So QB will be maximum for this. The right answer will be QA is maximum, no, this won't be the answer. QB is maximum, yes, this is what the answer we are getting. So QC is maximum, no, and rest all the three are unequal. So they cannot be equal. This is how we have to proceed. Here we have used both the laws, Stephen-Boltzmann law and also Wien's displacement law. We have used both the concepts in this one question. Pretty interesting question. We need to find which one is maximum. So we'll find the proportionality and we'll proceed in this way. So after practicing this, let's go with the next question of the class. Question number 7. A composite block is made of slabs A, B, C, D and E of different thermal conductivities given in terms of constant K and size given in terms of length L as shown in figure. All slabs are of same width. Heat Q flows from left to right through the blocks. Then in steady state A, heat flow through A and E slabs are same. B, heat flow through slab E is maximum, and C, temperature difference between slab E is smallest. D, heat flow through C equals to heat flow through B plus heat flow through D. First of all, this question is a more than one choice correct. More than one option will be correct in this one. So it's a multiple choice question. In JEE Advanced Examination, question can be asked in which options will be more than one correct. So in those questions, if you mark all options correctly, let's say 3 options are correct in this. I don't know that which options are correct. Let's say A, B, C are correct option. So if you mark A, B, C, you'll be getting +4 marks. And if you mark only A or only A and B, you'll be getting +1 mark for each correct answer. That is one for this, you get +2 marks. You won't be getting all the marks. Next, if you mark only A, you'll be getting +1 marks. If you mark any incorrect option, suppose you marked A, B and D, you mark the incorrect, you won't be regarded any marks, you won't be rewarded any mark for this. The next thing you see here, we have various slabs attached here. It's a composite system. Now read this, how are their dimension? It says that these are the 5 slabs. They have different thermal conductivities and each of the thermal conductivities are given in terms of K. A is 2K, B is 3K, C is 4K, D is 5K, E is 6K. That is what is given. Next you see they are and size given in terms of length L. Their size is given in terms of length L. You see a B's length is given as 4L. You see 1L to 5L. You see how it's given 0 to 1L. So this is 1L. 1L to 5L. This is 4L. Then again 5L to 6L. This is 1L. Let me write down, if you are not getting from this diagram, this will be L, this will be 4L, again this will be L as per the given thing. Next, here also you can see 0 to 1L, this much is 1L. So I am going to mark it, this much is 1L. Now see 1L to 3L, so this will be 2L, and then again 3L to 4L, this will be 1L. So this will be 2L. And again this is L. This is what as per the dimension it's given. Next thing you see, it's given that all slabs are of same width. So width we are going to see, it's a 3-dimensional figure, but as per the representation it seems to be 2-dimensional, but it's a 3-dimensional figure. Heat Q flows only from left to right. So heat is flowing Q from left to right, from this end to this end through the blocks. In steady state, see what we need to decide. Heat flow through A and E slabs are same. So we need to find out the rate of heat flow through A and E, whether they are same or unequal, or they are unequal. Heat flow through slab E is maximum, so that is what we need to check. Temperature difference between slab E is smallest. Now we need to also find out the temperature difference across E. So if it's said that it's smallest, so you need to evaluate the temperature difference across each one of the slab. Heat flow through C is equal to heat flow through B plus heat flow through D. So C heat flow is equal to heat flow through B plus heat flow through D. So that is, in this question we need to find out what is the amount of heat flow through each of the slabs and what is the temperature difference existing across through each of the slabs. Quite complicated question. It's based upon the concept of conduction. It's based upon rate of heat flow through a conducting slab. In our regular class I have told you about the series and parallel combination. Here can you see that this slab is connected to these 3 slabs. So these 3 slabs you can say they are in parallel. Then again this slab will be in series with these 3 slabs. So first of all what we can do, I also told you the concept of thermal resistance, that is R equals to L by K, which I have told you. So first of all let us try to simplify this problem, let us try to evaluate each of the thermal resistance given for each of the slabs. We all know that this is a very good question, so you need to be very attentive for the next 5 to 7 minutes that the time will be devoting to solve this problem. Thermal resistance. So thermal resistance, we all know that R is equal to L by K. This is a general formula. So for the A slab, slab A, the length you see, the heat is flowing from left to right. The length that will be coming, that will be L. Now K is 2K, so let me put here L is the length, K is 2K. Now comes the area. Area will be, now see this is the, it's a 3-dimensional figure. I am just taking how to imagine the area. The width is given as W. You need to see what area you have to see. A's length will be this part you see, that will be 1L to 4L, so 4L, and width is same, so that will be W. Let's say the width is W, so 4LW will be this. So let me say W that I am using, that W is representing width, and since width is equal for each of the slabs, so that's why I am using one unique constant, that is W. For B part you see, resistance of B, its length, this is the B slab, its length is 1L, from 1L to 5L, that is 4L will be the length. So 4L is the length and K is 3K. 4L divided by 3K multiply by its area. Again you see its width will be W, that is what you can use. Now you see the area will be, this length is L, L into W, this length will be L, this width will be L into W. So you will be getting here L into W. So this will come out to be 4L upon 3KW, and here you were having L upon this L upon, and now see L will be cancelled out, so need not to use this, 4 upon 3 kW, and here you will be using L will be cancelled out, 1 upon 8 LW, 1 upon 8 LW, so we got this. Next you see RC, length of C again it will be 4L, length of C will be 4L, so let's use it as 4L, K of C, that's given as 4K, so let me use that 4K. Now area part again, this length will be how much? From 1L to 3L, I have already given, this is 2L, so 2L multiplied by W, 2L multiplied by W, LL will be cancelled out and 4 and 4 will be cancelled out, it will be 1 upon 2, it will be 1 upon 2 kW. This is what you are going to obtain here, 1 upon 2 kW. C also we read. Now for D you see it's a lengthy question, just concentrate here with me in the class. Length again, length will be this much length, I have mentioned is 4L. So for D part, let me do it here, resistance of D, it will be 4L divided by its thermal conductivity, that's 5K. Its area you see, this much part is how much, that's given as L, and width W. So area will be thermal conductivity 5K, area will be L into W. Once again for D area, why we have done L into W? L will be the length and width W, that is what we can see. That's actually in the 3-dimensional view you can see that this is W. That is what we are using. Next thing for E. Length you obtain, what's the length? Length will be only from here to here, 5L to 6L, that means 1L, and again its thermal conductivity is given as 6K. So L upon 6K, and area you just try to visualize. Area, this much length, that is from 0 to this 1L, 2L, 3L, 4L. 4L multiplied by W, you will be getting this. 4L multiplied by W, you will be obtaining this. This comes out to be 1 upon 24 kW. And here we have 4 upon 5. This you can write as 4 upon 5 kW. Lot of calculation, I know that you would be worried that to complete this sooner, we will do it as soon as possible. So we got the resistance in terms of LW, sometimes KW, LW here I have written, just change it, this will be KW. Now next thing you see, all this resistance that we have marked, those are given in terms of KW, 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 KW. For the making it simpler, you see we have to compare RA, RB, RC, RD, RE. So if I try to find out the ratio, RA is to RB is to RC is to RD is to RA. How we can find out the ratio? You see the ratio, this it will be 1 by 8 is to 4 by 3 is to 1 by 2 is to 4 by 5 is to 1 by 24. Again that will be complicated. What do you do? Multiply 120 every side. Why is that? Because every denominator, if you see 8, 3, 2, 5 and 24, you will get LCM as 120. So 120 if you multiply, you will be getting, if you multiply here 120, now KW is common, that can be cancelled out. So 120 by 8, you will be getting 15. Here if you multiply 120, you get 160. Here if you multiply 120, you will be getting 120 by 2, 60. Same for here, 120 by 5, you will be getting approximately 24 into 4, you will be getting that as 96. And then 120 by 24, that is 5, so you will be getting this as 5. So you have obtained this, the value, how the resistance are related. Now after getting this ratio, can we write RA is equal to 15R, RB is equal to 160R, RC is equal to 60R, RD is equal to 96R, RE is equal to 5R. We can write as if they are in proportionality in this way they are related, so we can write in this way. Now, after writing this, we have the value of resistance. We can see from the composite slab how they are connected. Now, I am going to draw an equivalent diagram, and before that what we do, take note till here so that I may draw the composite diagram at the other end. Take note till here. Okay, I believe that you would have taken down. Now see, this part is very much important. So I am keeping this and rest part I am rubbing. So let me rub this. And from here onwards, I am going to draw a simplified diagram. I hope that you would have taken down. And this part is required, the last result is required. So I am keeping it as it is. Now the diagram will be, if I draw in terms of resistance, this is for A, and then we have here B, then we have the C, and then we have D. This is how an equivalent diagram we can draw, and this is for E. So let me mark here as B, C, D and E. Let's say the heat current that has flown through A, that is H, it will distribute in B, C, D. Let's say this is HB and this is HC and this is HD, and here let's say again it will be H. Now one thing is quite same, that is, now see the current entering, the heat current entering, this will distribute and the same heat current will be leaving through E. So we can say that heat current through A will be equal to heat current through E. Heat current through A will be equal to heat current through E. We can comment this thing. So first option, if you see, heat flow through A and E slabs are same. Yes, because the entry and exit slab are same. So we can say yes. We have solved a lot, but directly you can also comment on this. A option will be correct. Second, heat flow through slab is maximum. Now again to comment on this, heat flow through slab is maximum, and how much it is, let us comment on that also. And now you see here, since heat flow is H here, it's distributed here in the three ends, so automatically heat flow through the slab E will be maximum, because that is what is flowing through the A and E part. So the heat flow through slab E is maximum, that will be the same, because the heat flow, rate of heat flow entering and that same will be exiting, so that will be maximum. So option number B is also correct. So A and B we are finding that is correct. Next thing you see, temperature difference across slab E is smallest. So we need to comment on this, whether temperature difference across slab E is smallest or not. For that, let me rub this part. Oh, I just rubbed this part also. RA was, if you remember, that was 120/8 around 15 R, and RB was 160 R, that is what we know. RA is 15 R, let me write here, RB is 15 R and RB is 160 R, and RC is 60 R, RD is 96 R, RE is 5 R. This is what we have obtained. Now next thing, how to proceed further. We need to find out the rate of heat flow. See this option from D, heat flow through C equals to heat flow through B plus heat flow through D. So we need to find out how heat flow B, C, D is related. We know that heat flow through B is to heat flow through C is to heat flow through D. This will be equal to 1 upon RB is to 1 upon RC is to 1 upon RD. Because they are connected in parallel, so inverse ratio will be applicable, so we can write down this. So this again we can write 1 upon RB, that is 1 upon 160 is to, this will come out to be 1 upon 60. Then again we can write this as RD as 1 upon 96. This is what we can do. So if you simplify this ratio, this will come out to be 9 is to 24 is to 15. This is what you can actually get, 9 is to 24 is 15. So heat flow will be flowing in this ratio. Now you see how to find out the heat flow through B. Heat flow through B can be written as, they are in the ratio this, 9 is to 24 is to 15. So we can write heat flow through B will be 9 upon 9 plus 24 plus 15 multiply by H, that is what we will be getting. This can be simplified as 24 plus 9 will give you 33, 30 plus 15, that is 48. So 9 by 48, this will come out to be 9 by 48 H. So if you 3 into 3 9 times and 3 into 16, so you can write it as 3 by 16 H. Next thing you see, heat flow through C, that will come out to be 24 divided by again 9 plus 24 plus 15, that is 48 H. So this will come out to be 1 upon 2 H. Heat flow through D, so 15 upon 48, I am using here 15 upon 48 H, 3 into 5, 3 into 16, it will get you 5 by 16 H. Now you see here, if you compare HB equals to 3 by 16 H, HC equals to 1 by 2 H, HD equals to 5 by 16 H. If you just add HB plus HD, that will equal to HC. Comparing all the three, you will be getting, this is separate, this is quite, more things are written separately. You can check, you will be getting HB plus HD is equal to HC. Check option number D. Option number D, if you check, heat flow through C, that is HC equals to HB plus HD, heat flow through B plus heat flow through D. So option number D is also correct. That is also we can comment. Next thing you see, we need to also find out the temperature difference across slab, whether it is smallest or it is what it is persisting. Temperature difference across, we need to find out across E. So why not to find temperature difference across each of the given resistance. So temperature difference, we know that that is equal to heat current, that is equal to heat current H multiply with resistance, that is equal to heat current H multiply with resistance, that is what we can use. So across TA, it will be equal to, resistance is 15R, so 15R multiplied by the heat current, that is equal to H. So this is what we know, because we all know that heat current, the rate of flow of heat current is equal to temperature difference divided by the resistance. So temperature difference will be heat current multiplied by resistance, so H into 15R, that is what we can do. So this will be 15RH. Less space we have, more thing we need to write, so that's why I am using all the available space. And let me rub this part, not required, let me rub this part. Next thing you see for temperature difference across B, you see the resistance of B is 160R, and again the heat resistance, that is HB. HB we have already found out, it is 3 by 16H. You can see here, it's 3 by 16H. So multiply here 3 by 16H. So you will be getting this as, now this will be getting 10 times 10 to the 30 RH. We got temperature difference across B. Across C, you will be getting this as 60R multiply with, you across C, HC is equal to 1 by 2H. So multiply 1 by 2H, you will be getting 30R H for this also. Temperature difference existing, that will be 30R. And similar for all on parallel, you can easily check that for TD also be getting 30RH. I will just show you this. This is given as 96R multiply by 5 by 16H, because 5 by 16H is for HD, 5 by 16H. Multiply, this you will get as 30RH. 6, this will get 6 times 6 by 30, 30RH you will be getting. For temperature difference across E, let me show you the heat current is H multiply with resistance, that is 5R. So 5RH you will be getting. 5RH is the temperature difference. So let's go ahead and let's check 5RH as the temperature difference. So from here, temperature across slab E is smallest. We are having across A is 15RH, across B, C, D is 30RH, and it's only 5RH across E. So C is correct. Now one more thing I have commented on heat flow, the current also, the heat flow through slab E is maximum. Heat flow, you see, that is the rate of heat current through E. If you see, that is through A it's H, through B it is different, that is 3 by 16H, and again it's different in the ratio, and for E again it's equal to H. So if I talk about heat flow through slab E is maximum, yes, it's maximum for this also. So all the options are correct in this question. So what I'm going to do, I'm going to just rub the entire part. It's a very interesting question. We took more time to comment on this. All the 4 options came to be correct in this one. And I hope that you had understood how we have done this. It's a very good question. Do revise after the class. That's required. And just after this, we'll be continuing with the next 3 questions. Those will be also much interesting questions. So I believe that you have understood this question, and you just see one thing. This is a very controversial statement in the option number 2. Heat flow through slab E is maximum. We got that heat flow through slab A and E is same, that is H, that is what I have told you. So in your option, since A and E both are maximum, so only E will be not maximum. So what you can do, you can only opt for A, C and D, and B you can leave because both A and E are having the maximum heat flow. So the best way to choose will be A, C, D for this question. Let's go ahead with the next question of the class. Question number 8. Black body of temperature T is inside a chamber of temperature T naught. Now the closed chamber is slightly open to sun such that the temperature of black body T and chamber T naught remains constant. It says that we have a chamber and it's an isolated chamber initially. We have a black body whose temperature is T and the surrounding temperature is T naught, that is what it's given. Now it says that it is open to sun. It is open to sun such that temperature of black body and chamber T naught remains constant. Now, if temperature remains constant, we all know that what will happen. That means all the amount of heat energy that is incident, the same amount will be radiated. Whatever is incident, that is will be radiated. That is what happens when temperature remains constant. First option A, black body will absorb more radiation. B, black body will absorb less radiation. C, black body emit more energy. D, black body emit energy equal to energy absorbed by it. This is actually energy absorbed by it. You can take this. Now that is what I have told. Since temperature is constant, so black body will absorb more radiation? No, its temperature is constant, so this is invalid. Black body will absorb less radiation? No. Invalid. Black body emit more energy? No. Black body emit energy equal to energy absorbed by it. That is what will happen when the temperature remains constant. That is what I have taught you in our regular session. So option D will be the right answer for this. Let's go ahead with the next question of the class, 9th. 2 spherical bodies, A radius 6 cm and B radius 18 cm, are at temperature T1 and T2 respectively. The maximum intensity in the emission spectrum of A is at 500 nanometer and in that of B is 1500 nanometer. Considering them to be black bodies, what will be the ratio of the rate of total energy radiated by A to that of B? Total energy radiated by A to that of B, we all know that will be, it's a case of, if you see it's a black body or it's a different body, it says that 2 spherical bodies A and B are at temperature T1, T2 respectively. The maximum intensity in the emission spectrum of A is at this much and B is this much, considering them to black bodies. So this is given about black bodies, so we do not require emissivity. We can say that the amount of heat energy emitted per second will be equal to sigma A T to the power 4. That is what we can write. And we can also write that lambda m, that is at the maximum intensity, the lambda will be lambda m into T is equal to constant. 2 laws already we have discussed about these 2 laws. This is actually Stephen-Boltzmann law for black body. This is lambda m into T equals to constant, that is Wien's displacement law. Next thing, it's the rate. Now see about the area, it's given that there are spheres of different radius 6 cm and radius 18 cm. You see for A, the sphere is of radius 6 cm and for B, the radius is 18 cm. This is what that is being provided to us. It's a case of black body, so energy will be radiated. Now lambda into T equals to constant and lambda is given for both the bodies. It's required that, now lambda for A is given as 500 nanometer, lambda for B is 1500 nanometer. Let me write down. Here I am writing the lambda at the maximum intensity, that is 500 nanometer, and here for lambda B it's 1500 nanometer. That is what that has been provided. Next thing you see, consider that black bodies, what is the ratio of the rate of total energy radiated by A to that of B? Ratio of total energy radiated by A to that of B, so that will be equal to QA by QB, and that will come out to be A, area for A, T to the power 4 of A and area for B, T to the power B, TB power 4. This is what we can. Variables are the usual meaning. A means area for A, AB means area for B. It's a sphere. It's a sphere. So the area exposed will be 4 pi r square, proportional to square of the radius. So this we can write as RA whole square upon RB whole square. Now what about temperature? Lambda into T is equals to constant, so temperature will be inversely proportional to lambda. So we can write that this can be written as lambda B to the power 4 divided by lambda A to the power 4. This is what we can comment for the ratio of heat energy that is emitted. Now clearly all the values are provided, just we need to supply the values to get the answer. Radius of A, that's given as 6, radius of B, that's given as 18. So 6 square by 18 whole square multiplied by lambda B. You see the maximum intensity lambda that is given as for B is, I have noted down 1500 nanometer. And now see 1500, 500, 2 zeros also there, that will be cancelled out. So can we use this as 15 whole square, and this we can use as, and this power 4, it's not square, it's power 4. And here we can use as power 4. Now clearly we can simply solve this. You will be obtaining 15 by 5 will give you 3. This will become 3 to the power 4. Let me write down here. So you will be getting, now see here, this will be equal to 3 to the power 4 due to here 6, and this will get here 3 to the power 2. This is what you are going to obtain. 3 to the power 4 and here going to obtain 6, 3. So you will be getting 3 to the power 4 upon 3 to the power 2. So finally you can easily obtain the result. So what do you do? Take note till here. Let me write at the other end, take note till here. So clearly I believe that you would have obtained the required result for this 3 to the power 4 upon 3 square. That's clearly giving us 3 square. That is equal to 9. So the ratio in this case that you need to mention, that should be equal to 9. It's an integer type question. You can see that it's integer type question. The ratio you need to mention, that will come out to 9. So you have to encircle the bubble that is covering the digit 9. So go ahead for the bubble 9 and you need to encircle this as the answer. This will be right answer 9 for this ratio. So even for ratio also, if you get an integer, need not to worry, you need to mention 9:1. So you have to actually only bubble the circle carrying the digit 9. Next thing, let's go ahead with the next question of the class. That is question number 10. Two identical conducting rods are first connected independently to two vessels, one containing water at 100 degrees Celsius and the other containing ice as 100 degrees Celsius. In the second case, the rods are joined end to end and connected to the same vessel. Let Q1 and Q2 gram per second be rate of melting of ice in the two cases respectively. The value of Q1 by Q2 is. So here we need to check what is the amount of heat energy generated, that is, what is the rate actually we need to find out how, at which rate they are actually melting. So first of all, let me give you, we all know that the amount dq is equal to L into dm, that is what we can write. dq equals to m dm into L, that is what we can actually mention. Next thing you see, we all know that rate of heat energy transfer dq by dt is equal to temperature difference divided by heat resistance. This is what we know about it. Rate of heat energy actually transfer, that will go temperature difference from divided by heat resistance. Now from here, can we actually relate these two equations and actually try to relate the dm with temperature difference upon heat resistance? Now here if I divide this thing by dt, I will be getting dq by dt is equal to L into dm by dt. Clearly we can mention here dq by dt equals to L dm by dt. Next thing you see, we can go ahead and we can write that L dm by dt will be equal to temperature difference divided by heat resistance, that is R. So this we can reach up to this equation. So take note till here, let me write at the other end, take note till here. So here if you see it's L dm by dt, because L is constant, temperature difference will be constant. So can we write dm by dt is proportional to dm by dt is proportional to 1 by r, that is inversely proportional to r, or we can say that q given, that will be inversely proportional to r. So in the first case, you see the rods will be in parallel connection. In the first case, two identical conducting rods are first connected independently to two vessels. That is, they are connected in parallel. So in first connection, they are connected in parallel. In first connection, rods are in parallel. And in second, they are in series. In second, they are in series. So clearly we can say if R is the individual thermal resistance of each, and each will be R, each are identical, so each thermal resistance will be R and R. That is what we can actually comment on it. So we can write Q1 by Q2 for parallel, and so before that, for parallel, the net heat resistance will come out to be R by 2. For series, we can say it will be equal to R plus R, that is equal to 2R. So finally we can comment on Q1 by Q2 for parallel. It's R by 2 we need to mention in the denominator because it's inversely proportional to R, and for series you mention it here 2R, you will be getting 4 by 1. So clearly you see the required thing is, let Q1 and Q2 gram per second be the rate of melting of ice in the two cases respectively. The value of Q1 by Q2 is, Q1 by Q2 comes out to 4 by 1, and here it's an integer type question. Again I told in the case of ratio, when you get 4:1, you need to check the integer which is matching, you need to bubble this which is carrying the digit 4. So here we have got the result for this question also. So an interesting exercise we have practiced in thermal properties of matter. We can see that in JEE advanced exercise, in JEE advanced examination, how complicated questions can be framed based upon simple concepts that we have learned. Based upon heat transfer, we have seen so many questions based upon actually radiation, Stephen-Boltzmann law and Wien's displacement law we have combined, we have framed one question. So examiner can ask you anything. You need not to escape the chapter, you need not to actually leave this chapter. You are thinking that it's basic exercise, it's a basic chapter, so practicing only a simple question will not fulfill the target. What you do, practice more questions, see what previous questions have come. See this exercise, how beautifully we have discussed all the 5 and all the 10 questions in total for this JEE advanced pattern exercise. So be connected with us. I will be getting in touch with you in the next class with more concepts, with more discussion. Till the time, wishing you all the very best, and thank you everyone.